Hello everyone. Welcome to the next lecture on the numerical linear algebra. Today I will explain you the concept of single value decomposition. What is the physical significance of the single value decompositions and how this method is applicable for the matrix. So that will explain in this lecture. Myself Dr. Harish. You can follow and subscribe my YouTube channel where you can find the playlist of numerical linear algebra. You can see our last lecture was on orthogonal vectors, orthonormal basis, QR factorization, and many more lectures available in this complete playlist of the numerical linear algebra. Now, what is the overview of the single value decompositions and why there is a need of the single value decomposition? That's a very important question arises. We all knows in the linear algebra, we all knows whenever you have matrix called as a square matrix n cross n, then we can write any symmetric n cross n matrix as A is PDP inverse, where this capital D is known as the diagonal matrix, while this P is called as invertible matrix, where P is the any invertible matrix that we all knows up to the linear algebra. But remember students, this result is applicable only for the symmetric n cross n matrix, as P is a matrix and D is my diagonal matrix, and P is the matrix whose elements or whose columns are my orthonormal basis. But make sure this result is applicable only for the n cross n matrix. Or in other words, whenever you can say P is my orthonormal matrix, that means P transpose into P is my identity. Therefore, I can replace the value of the P inverse because P transpose into P is identity. That means P inverse will be my P transpose. Fine. As I mentioned you, this result is applicable only for the symmetric n cross n matrix. But the question arises is, what will happen if you have m cross n matrix? So clearly say this is not the square matrix. Then we can extend the result of matrix A PDP transpose to the m cross n. We are using the concept of single value decomposition. Is it clear why there is a need of the single value decompositions? That means we can generalize the concept of the transformations PDP transpose to the single value decompositions. In this generalization, we can consider any matrix. It may be square, it may not be. Now, what is the single value decompositions of the matrix A, which is of the m cross n matrix? We can write, we can transform, or we can replace the P to be the U, P transpose to be the V transpose, and the diagonal matrix I can written or denoted by the term sigma, where U is my, there are the m rows, so U is my m cross m matrix, V is my m cross, V is my n cross n matrix, and the sigma is my m cross n matrix known as diagonal entries. I will explain you the each concept, what is orthogonal matrix, diagonal entries in this lecture as well. So you can watch this video till the end, and I hope you can like and subscribe my YouTube channel. Whenever we are talking about the matrix m cross n, that means we are calling as A is my transformations, whose n is my number of the columns, 2 number of the rows. That is my transformations whenever we call as the matrix. Let's start with this. So in general, we have a matrix A, then we can write the single value decompositions as U sigma sigma V transpose. What is the meaning of the U? Fine. Our target is to know what is the physical significance of the mu, U, what is the physical significance of the sigma, and what is the physical significance of the V transpose or the matrix V. What is the physical significance of these three matrices? The physical significance of the U is it tells us about how it tells us about the peoples, or in general what are the various preferences about the matrix or the terms. Similarly, sigma is tell us about how important the each factor is. And the lastly, V will tell us about the products. That is, if you call as a matrix, this is my matrix. So this is a matrix corresponding to the certain elements or certain products. So the V will tell about how similar they are each other. I will tell you with the help of the example. Suppose the two movies, movie A, movie 1 and movie 2 are rated by the three candidates, Harish, Roji and Misty. Fine. And Harish has given 2 marks, 2 ratings of the movie 1, while 5 for the movie 2. Similarly, the Misty will give 3 and 5 for the rating 1 and 2. Now, what does the meaning of the single value decompositions in this particular example? Now, our target is to identify what is a U, what is my sigma, what is my V. Fine. The sigma, as I mentioned you, what is the U? U will tell us about the peoples in the preferences. So in this case, the U will tell us about the people preferences, like Harish, Roji and Misty will give you the preferences. Sigma, sigma will tell us about how the each factor play a role, that is how the importance of the each movie, and how these two movies are similar to each other, that tell us about the factor V. So this is the physical significance of the single value decompositions. Now, in order to understand the concept of single value decomposition, we need to understand the each term, that is the U, sigma and V separately. So for that, we need to understand the concept of eigenvalues, what is a symmetric matrix, what is a orthogonal matrix, and what is the meaning by singular values are there. So let's explore each concepts one by one. So firstly, let's explore what is the meaning of the eigenvalues in the single value decomposition. We will see, once we will complete this lecture, we will see the U is nothing but the eigenvectors of A into A transpose. V is nothing but my eigenvectors of A transpose into V, and sigma is nothing but my diagonal matrix with the singular values. So firstly, let us tell you what is the meaning of the eigenvectors of A into A transpose. Make sure, students, whenever you have any matrix A, whenever you have any matrix A, then we all know A into A transpose is symmetric matrix always. Fine. The first concept is, whenever you have any matrix A, that is a M cross N, then the matrix A into A transpose is symmetric always, and the matrix A into A transpose is called as Gram matrix. How you can prove that the matrix A is symmetric? In order to prove that the matrix A is symmetric, you need to prove that A transpose into A is at A. So let's start with A into A transpose. Fine. And we all know what is the value of the AB transpose. How you can write that? This number is my B transpose, A transpose. I can write this number is A transpose of transpose into A transpose. Transpose of transpose will be A into A transpose. What does it meaning? You can see what does it means, which implies A into A transpose is symmetric matrix. Fine. Similarly, you can prove that A transpose into A is also symmetric matrix. Fine. Another concept. This is the first concept that we will use everywhere in the single value decomposition. Second is, whatever the eigenvalues, or you can say if you have any matrix M cross N, the matrix A transpose A and the A into A transpose are always positive semi-definite matrix. What does the meaning of the positive semi-definite matrix? That means their eigenvalues are always greater than equal to 0. Fine. So let's start with the first result, that is eigenvalues of the A transpose A and A into A transpose are real and always a non-negative. Make sure, because the matrix A into A transpose both are my symmetric, fine, and we all know the eigenvalues of the symmetric matrix are always real, but it's a positive semi-definite, so the eigenvalues are always non-negative. The first result is that if lambda is eigenvalues of the A into A transpose, then lambda is greater than 0. Fine. The proof is a very simple. What does the meaning of, if I say if lambda is the eigenvalue of the matrix A, what does it implies? That implies the characteristics equation A minus lambda I will be 0. Fine. Or you can say Ax is equal to lambda x, where x is my non-zero eigen vector. Fine. X is a non-zero eigenvector of the A. That's the meaning of the eigenvalues. For more details, you can watch about the concept of eigens value. I have solved 20 plus, or I think 25 plus examples which are available in this playlist. Let me show you where are there. You can find the eigenvalues concept in this lectures. चलिए, let's start with this. Let x is the non-zero eigenvector of A transpose into A. Fine. Whose eigenvalue is lambda. That means I can say A transpose into A, lambda is, by using this definition, Ax is equal to lambda x. So I can say A into x is lambda into x. Fine. Now in order to prove lambda is a greater than 0, I can start with a norm of A transpose A. Clear? Let's start with the A transpose of A, or Ax. Whenever you are talking about the norm of Ax or norm of A, I can written this number is A transpose into A, or we can say A into A is A transpose into A. So I can write, again this is the matrix, so I can write this number is X transpose into A transpose A of X. Now clearly say what is the value of X transpose A of X, because X is my eigenvector of A transpose. So by the definition of the eigenvector, A of X is lambda of X. So I can write this number is lambda into X, because lambda is the real which is come outside. I can write this number is X transpose into X. So by using this norm definition, sorry, it's a square, I can write this number is norm of X square. Fine. Now because by the definition of the norm, we all know norm of the x square is always greater than 0, which implies lambda into norm of x square is always greater than 0. And norm of x square is always a positive. So when it will be positive, it is positive only when lambda is my greater than equal to 0. So that means the first result is the eigenvalues of the A transpose A are always greater than equal to 0. Similarly, you can prove that if lambda is the eigenvalues of A into A transpose, then it is always greater than equal to 0. Second concept, whenever you have a matrix M cross N, then A transpose A and A into A transpose have the same set of the positive eigenvalue. What does it mean? Let's say A is my 1, 2, 3, 4, 5, 6. Fine. This is my 3 cross 2. Then clearly say if you write A into A transpose and A transpose into A. Fine. What is the matrix of A into A transpose? This number will be my 3 cross 3, and A transpose into A, it is my 2 cross 2. Then clearly say the matrix A into A transpose has 3 eigenvalues, while the matrix A transpose A has 2 eigenvalues. And this result says both the matrix has the same positive eigenvalues. The meaning, if I say the A into A transpose has eigenvalue 4, 0, 3, fine, then there is no need to compute A transpose of A because there are the two positive eigenvalues. So A transpose of A must have 4 and 3 are the eigenvalues. Fine. The proof is a very simple again. If I consider, let n of A is the set of all those positive eigens values, then what is your target? Your target is to prove positive eigenvalues of A transpose A is same as number of the positive eigenvalues of A into A transpose. Clear? So let's start with the first value. So let X is the eigenvector of, let's say, A transpose into A, whose with eigenvalue lambda. Fine. Or you can say let lambda belongs to the n of A transpose A. Fine. Let lambda is the eigenvalues of the A transpose A. What is the meaning of lambda is the eigenvalues of A transpose A? That means this equation will satisfy. Fine. Remember student, ये वैसे ही लिख रहा हूँ, that is a AX is equal to lambda x. In this case, instead of the matrix A, it has A transpose A. Now let's start with this. We can start from the A transpose of A. Fine. Once you can say, then A is my m cross n. Then what is the value of the AX? AX belongs to the dimension Rn, because once you can say A is my m cross n, that means the matrix A is my Rn to R of m. What does it implies? A of x belongs to the R of n, is the part of Rn. Is it okay? Now, once we know AX is the part of the Rm, then we can start with the number of the positive eigens value. I can start with the A transpose. If I open them, it's A transpose of AX. Now by the definition of the eigenvalue, this number I can written as A transpose of AX is equal to lambda x. If I substitute the value, this is lambda x. Lambda is the outside, which is nothing but my AX. Fine. Similarly, if I assume lambda belongs to the number of the positive eigenvalues of the A into A transpose with a non-zero eigenvector x. Fine. Or you can say lambda is the eigenvalue of A into A transpose. Similarly, I can start with the second one. In that case, A transpose of the x belongs to the Rn, and hence I can start with the A into A transpose into A of x. Fine. So if I start with this case, you can see if I open this bracket, what does the meaning of A into, so that number means A into A transpose of x is lambda x. I can substitute the value is a lambda x. Now from the equation number 1 and equation number 2, we can see lambda is the eigenvalues of A transpose A. Lambda is the eigenvalues of the A into A transpose. Hence, both the sets have the same positive eigenvalues. Why positive? Because in the first result, we have proof lambda is always positive number. Now, what are the common properties between them? Clearly say, if A is my m cross n matrix, then if A is my m cross n, what is the A transpose? This number is n cross m. Then what is the A transpose into A? This number is n cross m. And this number is m cross m. Is the A transpose A symmetric? Yes, this is symmetric. Whether A into A transpose is symmetric? Yes, it is symmetric. All the eigenvalues of the of the matrix A transpose A real? Yes, all the eigenvalues are also real because they are symmetric. Non-zero eigenvalues of the A into A transpose is the same. Fine, they are also same. This is non-zero. And what is the zero eigenvalues? Zero eigenvalues, it may be differ depending whether m is greater than n or n is less than m. Fine. So may differ depending upon the rank and the dimensions, that is the value of the m and n. Is it okay? The non-zero eigenvalues of the A transpose A and A into A transpose are always same. Now, this is about the A into A transpose and A transpose A. Now let's discuss the concept of the singular value. The singular value is totally depends upon the eigenvalues. Fine. So that means whatever the matrix A is given to you, our target is to find the eigenvalues of the matrix A. The first definition is, if I consider lambda 1, lambda 2 and lambda n is the eigenvalues of the matrix A into A transpose, then we can write this matrix in the increasing order. Fine. Or you can write in the decreasing order. That choice is on your side. Okay? Then we can define the symbol sigma I, which is as positive square root of the eigenvalue, and that sigma I is known as singular value. That sigma I is known as singular values. So if I define the positive square root of the lambda i's, that is eigenvalues, then the lambda 1 is corresponding to the sigma 1, lambda 2 is corresponding to the sigma 2, and these sigma i's is known as singular values of the matrix A. Remember, your target is to find the eigenvalues of A into A transpose, not for the A, because A is your M cross N matrix, while A into A transpose is my square matrix. And once you have the square matrix, then only you can find the eigenvalues of the matrix. And the previous result we have seen that the matrix A into A transpose and A transpose into A have the same non-zero eigens value. So for example, if I consider A is my 1, 2, 2, 1, then how you can find the eigenvalues of A into A transpose? So firstly, let's say what is the A into A transpose? 1, 2, 2, 1. And if you find the transpose 1, 2, 2, 1, then this matrix will be 1 and 2, 4 is 5, 2 plus 2 is 4, 2 plus 2 is 4, 4 plus 1 is 5. So therefore, the characteristics equation of, because your target is to find the eigens value, so how you can find the characteristics equation? That will be 5 minus lambda, 4, 4, 5 minus lambda is equal to 0. Can you write the equation? 5 minus lambda square minus 16 is equal to 0. So if you open this bracket, lambda square minus 10 lambda plus 9 is equal to 0. Hence, the value of the lambda is my 9 and 1. Fine. सबसे पहले बड़ी रकम लिखनी है आपको. Find is a 9, 1 are the eigens value. Once you know the eigenvalues is a lambda 1, so therefore sigma I, or because there are the two eigenvalues, so sigma 1 and sigma 2. Sigma 1 is the positive square root of the 9, sigma 2 is the positive square root of the 1. That means 3 and 1 are the eigens, where are the singular value of the matrix 8 into A transpose. Always remember that, because in this case the number of the non-zero eigenvalues are my 2. There are the two non-zero eigens value. Hence, you can say the rank of the matrix is my 2. Fine. So the number of the non-zero singular values of the A is equal to the rank of the matrix A. Now, once we understand the concept of the singular value, Fine. Once we know understand the concept of the A into A transpose and A transpose of A, and the third thing is we know the concept of the eigens vector of the matrix, then we can define the formal definition of the single value decomposition. If A is your m cross n matrix with the singular value sigma 1, sigma 2, sigma n is greater than 0, then we can define R as a number of the non-zero singular values. Fine. Or you can say R is, because it's a non-zero singular value, we can say R is the rank of the matrix A. Then we can define the single value decomposition is U sigma V transpose, where U is my M cross N matrix, V is my N cross N matrix, and sigma is my N cross N matrix. Now because R is my rank, so I can say it's a sigma of R, rest values are 0, where sigma of R is my diagonal matrix with the elements singular values, sigma 1, sigma 2, rest all the values are my 0. Fine. Where sigma is my sigma of R, that's the values in the diagonal entries are my sigma is, and the rest all values are my 0. As it's a similar case as we define for the single value as we define for the symmetric matrix. What is the D? D is the diagonal matrix. Fine. And how you can define the diagonal matrix? With the eigens values only, because it's a symmetric matrix, so this also is n cross n. But here we are talking about the generalization of the matrix. And U and V are the orthogonal matrix of the size m cross m, that is the number of the rows, and n cross n is the number of the columns. Now next we will define the orthogonal basis of the U and V. Fine, that is called as the eigen vectors. If I call as V1, V2, Vn are the orthonormal. Fine. To understand, remember students, always remember to understand the deeper concept of the orthonormal, you can watch about my previous lectures, orthonormal vectors and orthonormal basis. अगर मैं quickly से recall करूं, what is the orthonormal basis? Orthonormal basis means Vi dot Vj is my 0 for all I is not equal to j. This is the first property. And the second property is norm of the Vi is my 1 for all I. Once these two properties are satisfied, we call as the orthonormal basis. And Vi is the eigenvector of the A transpose A. What does it mean? A transpose A is my matrix. Vi is my eigenvector. What is the eigenvalue corresponding to Vi? Is my lambda I, and we have defined the singular value is positive square root of lambda I, that means sigma I square of Vi. This is given to you. Fine, this is given, and the orthonormal basis. These 2 points are given to you. Then we prove that A into Vi, what is the matrix A? A is my R cross M cross N matrix. The norm of A into Vi is my sigma I, and A of Vi and Vj are orthogonal matrix. What is the meaning of the orthogonals? That means the dot product of the two elements xi, yi is my 0 for all I is not equal to j. इसलिए मैं कह रहा हूँ you must watch about my these two lectures, orthogonals and the orthonormal basis. So let's start with this. Vi's are given to be the orthonormal, hence we can say that dot product is 0, norm is 1. So let's start with the first one. We can start with the A of Vi square, because it's a norm, so I can define this number is A of Vi transpose into A of Vj. I can start with the Ai into Aj. Fine, Ai into Aj. So that number I can define as A of Vi transpose A of Vj by using the standard inner product. How you can open that? It's a V transpose of I, A into transpose, A into Vj. Now, by using the concept of A transpose A, Vi is the eigenvector of Vi is the Vj, or Vi is the eigenvector of A transpose A. That number I can written as sigma I square Vi. I can substitute the value. So Vi transpose this number, because it's a Vj, so that number is my sigma j square into Vj. Sigma is a positive real numbers, so I can take it as the outside. This number is my Vi transpose into Vj. Now Vi into Vj is my 0, fine, or sigma j square. I can written this number is Vi dot Vj. Always remember, my definition is x dot y is x transpose into y. Fine. Now, because Vi into Vj is my 1, for all I is not equal to j, Vi into Vj is my 0, and whenever I is equal to j, the norm of Vi, that is a Vi into Vi is 1, so this number is my sigma j square. So left hand side becomes A dot Vj. So from here you can see whenever I is equal to j, the left hand side say A of Vi square, norm of Ai into Vi, norm of sigma j. So first result hold. And from this case, whenever I is not equal to j, A of Vi into A of Vj is 0, which implies the matrix A into Vi, A into Vj are orthogonal matrix. Fine. So that's the proof of this first and second part. Now, we have known once we have the orthogonal basis, we can extend them to the orthonormal basis. How? Remember students, if you have the u1, u2, un, these are my orthogonal. Fine. These are my orthogonal basis. Then we can extend it. We can define the orthonormal. We can define the orthonormal basis. How? Very simple. We can divide the u1 with its norm. We can divide the u2 with its norm. Similarly, for the un, we can divide with its norm. And this basis is known as orthonormal basis. Now, since we have proved that A of Vi and A of Vj are orthogonal basis, hence we can say A of Vi divided by norm of A of Vi are my orthonormal basis. Fine. Or in other words, you can say what is the norm of A into Vi, that is a sigma I. So then we can say A of Vi divided by sigma I is my orthonormal basis. Fine. So I can define the orthonormal is my Ui, or you can say this number is A of Vi divided by sigma I. Is it okay? Now, and since A is my what is the A of Vi? A of Vi is the part of the Rm, hence Ui is belongs to the codomain element. Now, once we have the orthogonal, because A is my m cross n, so it's a part of the column. How you can extend it to the complete Rn? How you can extend it? By using the Gram-Smith process. We can extend it to the complete elements by using the Gram-Smith process. Now clearly say, because what is the value of the sigma I? Sigma I is the positive roots of the lambda I. Now, and Ui are my orthonormal. So if I multiply both sides by Ui, I can write this number. Fine. What is the sigma? What is the root of sigma? Root of the lambda. Can you write this number is A of Ui, or you can say A of what is the lambda is the A of Y. You can see what is the norm of A of Vi. Norm of Ai is sigma I. Sigma I is nothing but lambda I. Fine. I can multiply this equation by Ui. What will happen if I multiply this equation by Ui? This is sigma I ui, which is root of lambda I ui. That is up to here part. Fine. I can substitute the value of the ui. Then you can see norm of ui will be cancelled. It becomes a of vi. Or in the matrix format, or in the matrix form, what is the a into v? Because v is my column vectors, v1, v2, and so on. So you will get a of v1, a of v2, a of vn. And u into sigma is u1, u and ur are my rank of the matrix. If you multiply them, what will happen? That will be ui sigma I 0, 0, 0. Fine, that is a summation. Clear? So that number is itself defined as sigma 1 u1, sigma 2 u2. Why? What is the value of the sigma r? As I define u, this is the diagonal entries corresponding to the singular values. And again, it is my sigma ur, so you can multiply them. From these two equations, what you obtained, which implies AV is u sigma. Now you can multiply both sides by V transpose. Find u sigma V transpose. Now because V is my orthonormal, fine. Once V is my orthonormal, what is the meaning of that? V into V transpose is identity. This number is my identity. Hence, A is U V V transpose. Now, the result we have defined, UI is AVI, UI is AVI divided by sigma I is basically my unit vector. Fine. Unit eigenvector of the A into A transpose. The proof is again very simple. Your target is to prove norm of UI is 1. This is your target. Fine. I can start with the UI dot uj, which is defined as ui transpose into uj. I can substitute the value of the ui is a of vi sigma I, where ui is a vi divided by sigma I. Make sure vi's are my orthogonal basis. Fine. And sigma I is my singular values. It is always a positive values. So let's start with the norm of ui. I can write this number is ui transpose into ui. You can substitute the value of the ui is a of vi divided by sigma I transpose into a of vi divided by sigma I. Because sigma I is the positive real value. So once it's a positive real value, then sigma I transpose is nothing but sigma I. So the denominator becomes sigma I square. While for the numerator, I can write this number is Vi transpose A of Vi. Fine. Now you can see what does the meaning of this bracket. A transpose A into Vi. Can I write this number is lambda I into Vi? Can you write? Yes, because lambda I is the eigenvalues of A transpose into A. Fine. Or lambda I can also written as sigma I square into Vi. I can substitute in the numerator. It's a Vi transpose sigma I square into Vi divided by sigma I square. Sigma I square will be cancelled. It is a Vi transpose into Vi, which is always 1. Why? Because VI's are my orthonormal basis. Once they are the orthonormal, what does it mean? Norm of the VI is my 1. So therefore, norm of UI is 1. Hence, UIs are my is the unit eigenvectors of the A into A transpose. So what is the summary of the single value decomposition? If you have the matrix A, you will inform us the orthogonal matrix, which are defined as 1 over sigma I A into Vi. Capital sigma is my matrix composed of the singular values. Fine, where sigma of R is my rank of the matrix, and V is the orthogonal matrix of the A is the orthogonal matrix, and the elements of the matrix is called as eigens vector of the A transpose A. What is the procedure to write the any matrix A into the single value decompositions? We can start with the matrix A, find the eigenvalues of the A into A transpose. We can find the A into A transpose and A transpose A. Always remember A transpose A and A transpose both are my symmetric matrix. Always. And they are always my square matrix. We can find the eigenvalues of the A into A transpose, the non-zero eigenvalues of the A into A transpose, and A transpose into A are always same. We can find the eigenvectors. We can find the singular values. Fine. Then we can define the value of the U. How you can find the value of the U? For that, we can firstly find the value of the V, because Ui is my fine. So we need to firstly find the value of the Vi. Vi is the eigenvector of Vi are the eigens vector of A transpose into A. We can find the eigenvectors of the A transpose A. Based on the value of the Vi, we can find the matrix U, and whose elements are AVI divided by sigma. And then we can write the matrix A is in terms of U sigma V transpose. Fine. So this is a very simple procedure of the single value decomposition. I will explain you with the help of the several 20 plus examples how you can write any matrix A into the single value decomposition in the next lecture. Let me know in the comment box, are you interested to find the lecture on the examples? Then I will upload the lecture very soon. Till then, you can share this video with your friends, like and comment on the videos. Best of luck, students. Happy learning.